Hi guys, Daniel here. Hope you're doing well. Hope you guys are studying hard as exams get closer and closer. So today we've got paper 3 of the Edexcel A-Level Maths June 2023 series, Mechanics. And having done this paper along with stats and both pures, I definitely think this is the easiest paper out of all of them. There were definitely some tricky parts, especially maybe the projectiles in question 5 and then obviously moments in question 6. But I think from questions 1 to 4 was pretty straightforward. You guys can let me know what you think of it anyway. And yeah, again, you will have the timestamps in the description, so you can just easily go to whatever question or a specific part of a question quite easily. And yeah, that's pretty much it from me. Let's get into it. Okay, so question 1 says a car is initially at rest on a straight horizontal road. The car then accelerates along the road with a constant acceleration of 3.2 meters per second squared. Find for part A the speed of the car after 5 seconds for 1 mark. Okay, this is just standard Suvat. So remember, first thing you're going to do is you're going to write out Suvat. So you're going to write S, you write U, you're going to write V, you're going to write A, and you're going to write T. And then let's look at what we've got here. It says that the car is initially at rest. We know that means that U is equal to 0 here. So I'm going to U is equal to 0. It says that the car then accelerates along the road with a constant acceleration of 3.2. So I'm going to say A is equal to 3.2. And we need to find the speed of the car. We need to find the speed, right? That's V. So we're looking for V. After 5 seconds, that means T is equal to 5. So we've got these four variables here. You ask yourself what formula connects all of these four together, and that's just V is equal to U plus AT, isn't it? So plugging in everything that we know, it's going to be V is equal to 0 plus 3.2 times by 5, which is 16. So therefore, we could say that V is equal to just 16 meters per second. That's fine, that's done, that's part A. And in part B, it says we need to find the distance traveled by the car in the first 5 seconds. Again, we're looking for the distance, so we're looking for S. We know from part A that A was equal to 3.2. We know that T is equal to 5. And remember, it was from rest, so U is equal to 0. So again, what formula connects these four variables together? That is just S is equal to UT plus a half AT squared. So now I'm just going to plug in everything here. So I'm going to be S is equal to 0 times 5 plus a half. And then A is 3.2. And then T is 5, so 5 squared here. And then I'm just going to plug this into my calculator. So it's going to be 0 times 5 plus a half. And then 3.2. And then 5 squared. And this is equal to 40. So therefore, the distance traveled in the first 5 seconds is just 40 meters. And that's question 1, finished. Okay, question 2 says a particle P has mass 5 kilograms. The particle is pulled along a rough horizontal plane by a horizontal force of magnitude 28 newtons. The only resistance to motion is a frictional force of magnitude F newtons, as shown in figure 1. Part A says we need to find the magnitude of the normal reaction force of the plane on P for 1 mark. Okay, so for this one, remember what you should always do first is to draw your force diagram, right? So what I'm going to do is let me just screenshot this here, screenshot this diagram, and I'll put this here. Okay, so we've got a couple of forces given to us already, but remember, we are dealing with a particle on the surface, so we know that there's definitely going to be a normal reaction force going vertically upwards here, so we can label this R. And then obviously we have a weight going downwards, isn't it? Now weight is equal to mg, the mass is 5, so this is going to be 5g. Now, part A tells us we need to find out what R is, the normal reaction force. So what we have to do here is just resolve vertically, don't we? So if we resolve vertically, we can see quite clearly that the reaction force is going to be R is equal to 5G here, which means that we have 5 times 9.8, which is just equal to 49 newtons, isn't it? So the reaction force, normal reaction force is just 49 newtons. And that's part A. Part B says the particle is accelerating along the plane at 1.4 meters per second squared. Find the value of F, the frictional force. Okay, so we've got this particle here, and apparently it's going this way at 1.4 meters per second. Now, remember with this one, you're trying to find out what the frictional force is. You're going to use Newton's second law, right? F equals ma. So what we're going to do here, I'm just going to zoom out a bit. Let's say part B. We're going to use F equals ma, where F is a resultant force right now. The way I look at this is particle P is moving to the right, and we have this 28 newtons driving force, right? So what will happen is that the 28 newtons will be dominant, will be the dominant force, and then the frictional force will be opposing it as it's driving forward, right? So we're going to have 28 take away f, and then this will equal the mass, which is 5, times the acceleration, which we know is 1.4. Now, tidying this up, we've got 28 take f, and we've got 5 times 1.4, which is just 7, isn't it? So we've got this here. And then now to get f, we're going to move the minus, we're going to minus 7 here. We're going to move the f there. That means that f is just equal to 21 newtons, right? So that's done. Part C, it says the coefficient of friction between P and the plane is mu. Find the value of mu, giving answer to two significant figures. Okay, so this is not too bad. Now remember the formula for friction, right? Friction is just equal to F is equal to mu R, right? And we need to figure out what mu is. Well, we know what F is. F is 21 from part B. And we know that R is 49 from part A, right? Meaning that mu is just going to equal 21 over 49. And what is this? 21 over 7 is 3. 49 over 7 is 7. It's just 3/7, isn't it? And they wanted it to two significant figures. So let's go ahead and do this. So 3 over 7 to two significant figures is going to be 0.43, isn't it? It's going to be 0.43. And that will be our coefficient of friction. And that's part C finished. And that's question 2 finished. Okay, so question 3 says, at time t seconds where t is greater than or equal to 0, a particle p has velocity v meters per second where v is equal to t squared minus 3t plus 7i plus 2t squared minus 3j. Find, part A, the speed of p at time t equals 0. Okay, so we've got the velocity vector here and they're asking us for the speed. So remember, the speed is just the magnitude of the velocity. So what you'd want to do is just plug in 0 into your velocity vector, and then once you've done that, just take the magnitude by doing Pythagoras. So let's go ahead and do that. So part A, we need the speed of t equals 0. So I'll plug in t equals 0 into this formula for the vector here. It will be v is equal to, the t's will disappear, so just be 7i, and then plus, and then that t will disappear, will just be minus 3j. Now this is the velocity at time t equals 0. To find the speed, we need to do the magnitude of the velocity. So we're just going to do Pythagoras here. So it's going to be 7 squared plus minus 3 lots, minus 3 squared. And then if I put this into my calculator, this will give us 7 squared plus minus 3 all squared. And this gives us root 58. So it'll be root 58. And to three significant figures, that would be 7.62. 7.62 meters per second. Okay, so we've done that. And part B now says we need to find the value of t when p is moving parallel to I plus j for 2 marks. Okay, this isn't too bad as well. And this comes up quite a lot when they ask you to find the value of t when it's moving in a certain direction parallel to a certain vector, right? Now, I plus j, if you think about it, right, if I was to just draw a little vector like this, I've got, let's say this is I, right? This is I here, and then j is right here, like this here. Now remember, I plus j, right, is just the same as 1i plus 1j, right? So in other words, right, we've got 1 unit here, 1 unit here. We know that the components are equal when we're traveling at I plus j. So if we're parallel, it has to be the same thing. So essentially what you're doing here is you're just going to equate the components for I and j, because that's when it will be traveling parallel to I plus j. So in other words, you're just going to just do t squared, and then what was it? T squared minus 3t plus 7, t squared minus 3t plus 7, and this is equal to 2t squared minus 3. 2t squared minus 3, and then you just solve this here. So doing this here, I'm going to move everything from left to right. This give me 0 is equal to t squared plus 3t, and then minus 10. Now if I put this into my calculator, it will give me, let's just do it very quickly, go to quadratic here. And oh, to be fair, it's actually quite simple, isn't it? It's just going to be 5 and minus 2, to be fair. Be t plus 5, right? And t minus 2, wouldn't it? Yeah, that would work. So that would mean that we'd get t is equal to negative 5, or t is equal to 2. And remember, t is greater than or equal to 0, so we can't choose negative 5. So the answer is just going to be t is equal to 2. And that would be that for part B. Another thing as well is to look at it as another way of doing part B is to say, well, if we're traveling parallel to I and j, then as we said, the components are the same, which would mean technically this vector here is traveling at a 45-degree angle to the horizontal, right? So what you could do is say, okay, well, maybe you can find an expression for tan, right? And we know that tan, just using SOHCAHTOA, tan 45 will just be equal to y over x, isn't it? So the component for j divided by the component for I, right? So we could just say 1 over 1 here. And now in our case, it was this one here. So it'd be 2t squared over this component. So I'll just do it here. Just do it here very quickly. So we're going to have tan 45 would equal the j component, right? Y, 2t squared minus 3 over the I component, t squared minus 3t plus 7. And we know that the tan of 45 is 1. So essentially, we're just making this equal to 1 here. And then if you solve this, right, you will just get exactly what we have here. And you'll get t equals minus 5 and t equals 2. So this is another way to do part B, just for anybody that did it that way. So yeah, that's fine. So we've done that. Now part C says we need to find the acceleration of P at time t seconds. Okay, so we've got the velocity vector given to us. To go from the velocity to the acceleration, we just differentiate with respect to t, don't we? So let's go ahead and do this on the next page. So let us just get a v again. So I don't need to keep going up and down. Let's put this here. And then let me just put this here. Okay, so remember, we need the acceleration. So we need to just differentiate with respect to t. So A will just be equal to, now differentiating this component here, we'll just have a 2t minus 3i, right? Plus, and then we're going to differentiate this component. It's going to just be 40j, right? So that's that done. That's part C. And then what it'll ask us for part D? It says find the value of t when the direction of the acceleration of p is perpendicular to I. So let me just copy this here as well. So we don't need to keep going up and down. So again, with these questions, especially with anything in A-level maths, right, just try and visualize what's going on. Always creating a picture will always help you, will aid you in answering the question, right? So this one here, we're trying to find the value of t when the direction of acceleration of p is perpendicular to I. Well, what is I? I, is just your horizontal component, right? I travels horizontally. If you are perpendicular to a horizontal line, you are just vertical. You're just traveling vertically upwards, right? So that means we're just traveling in the j direction. So in other words, if you're traveling in just in just the j direction, that means that your component for I would be 0, right? If you are traveling perpendicular to I, right? That means you're traveling vertically. So in other words, what we need to do is just make our I component equal to 0. Because when we're equal to 0, that means we're just traveling vertically upwards. In other words, perpendicular to I. So all you're going to do here is you're just going to say that if we're traveling perpendicular to I, that just means that 2t minus 3 must equal 0. And that just means that 2t is equal to 3, meaning that t is just equal to 3 over 2, or 1.5. And that will be our answer. And that is question 3 finished. Okay, so question 4 says a particle P is moving on a smooth horizontal plane. The particle has a constant acceleration for 2.4i plus j meters per second squared. At time t equals 0, P passes through the point A. At time t equals 5 seconds, P passes through the point B. The velocity of P as it passes through A is minus 16i minus 3j meters per second. Part A says we need to find the speed of P as it passes through B for 4 marks. Okay, so remember, this is just the vectors and kinematics, right? Part A is asking us for the speed. Now remember, the speed is just the magnitude of velocity. So what you'd want to do is work out what your velocity is, right? And then once you figure out your velocity vector, you're just going to take the magnitude of that and that'll give you the speed. So what do we have here? So let's just put this here. So we'll do part A here. Part A here. And then what does it say? It tells us that the particle has a constant acceleration of 2.4i plus j. So I'm going to just say A, we know it's 2.4i plus j. And what else do we know? They've told us that the velocity of P as it passes through A is minus 69 minus 3j. And I remember, when P passes through A, that's when T is equal to 0. So that must be your initial velocity. So we're going to just say here that our U is equal to minus 16i minus 3j. And what else do we know? we need to find the speed, right? Which means we're looking for the velocity, right? So I'm just going to say v is equal. And is there anything else that we know? Yes, we know the time when p passes through b is 5 seconds. So we know that t equals 5. So again, we're using Suvat pretty much in vector form. So you ask yourself, we've got these four variables here. Which formula do we know connects them? It's just a v equals u plus at, isn't it? So I'm going to say v is equal to u plus at. And I'm going to plug everything that I know here. So it's going to be v is equal to u, which we know is minus 16i minus 3j, and then plus a, which is 2.4, 2.4 I plus j, or 1j, and then times by 5, isn't it? Now, what we're going to do here is just work out what this vector is. So let's just tidy this up a bit. We can say that we've got v is equal to minus 16i plus, sorry, not plus, minus 3j, minus 3j. And then we've got 2.4 times 5, which is 12. So I've got 12 I here, and then plus 5j. So now we can just add these together. So we're going to v is equal to minus 16 plus 12 is going to be minus 4i, and then minus 3 plus 5 is 2, 2, positive 2j. So that means then that we've got our velocity vector. To get the speed, we know that speed is the magnitude of velocity. So we're just going to do Pythagoras on those. So we're going to minus 4 squared plus 2 squared. And then putting this into the calculator will give us square root of minus 4 all squared, and then plus 2 squared. This is equal to 2 root 5. So our speed is 2 root 5 meters per second, or to three significant figures, 4.47. 4.47 meters per second. And that is part A done. Now let's go to part B. Okay, so part B says the position vector of A is 44i minus 10j meters. At time t equals capital T seconds, where capital T is greater than 5, P passes through the point C. The position vector of C is 4i plus cj meters. Part B says we need to find the value of T for 3 marks. Okay, so what I'm going to do, I'm just going to screenshot the questions here, so we don't need to keep going up and down, right? I'll just paste it here. Okay, so we're here. Let me just make this very small so it can fit into the page. Okay, so we need to find the value of capital T, right? And they've given us the position vector of C. So what you're going to be doing here is just using your formula to calculate the position vector at any point, right, with vectors, right? So remember, to do this, you've got to remember the formula. If I want to express RC as a position vector, or RC will be equal to your initial position vector, right? Don't forget that. RU, I'm going to call it RU, plus RT, right? Where RT is just an expression for the displacement anytime after T, right? After T equals 0. So what we can do here is say, let's plug in everything that we know. So we know that RC is 4i, 4i plus CJ. And then this is equal to RU. Now, this is going to be your initial position vector. Now, remember, from part A, they told us that at time t equals 0, P passes through A. So our initial position vector is going to be A here, right? 44i minus 10j. So I'm going to put this here. This here is going to be 44i minus 10j. And then RT, right, is just going to be your position vector at any point in time for t, right? So it's going to be ut plus a half at squared. Now, we know u and a from part A. U was equal to minus 69 minus 3j. So I'm going to just say u is equal to minus 16i minus 3j. And a was equal to, I believe it was 2.4i plus j. 2.4i plus j. So therefore RT, right? RT will just be equal to UT, so minus 16i minus 3j t plus 1/2 and then 2.4i plus j and then t squared, isn't it? So now we can just plug this in here. So what I'm going to do actually, just so there's a bit of room, just going to move this down a tiny bit here, and then we'll just continue. So yeah, so now if I plug that in for RT, it's just going to be minus 16i minus 3j. And now remember, we're looking for capital T. So I'm going to change this to a capital T. And then plus 1/2 and then 2.4i plus j and then capital T squared, isn't it? So now we're here. Now remember, we know what the position vector of C is. It's 4i plus cj. Now, if these are two are equal, then what we could do potentially is maybe tidy these up to get the i's together and the j's, and then equate components, right? And hopefully we can form some sort of equation in T. So let's go ahead and do that. So first things first, let me just tidy this up a bit more. So we could say we've got 44i minus 10j. And in this one here, I'm going to get the i's together. So I've got minus 16, right? And I'm going to multiply by that t. That will give me minus 16 capital Ti for that I component there. And then if I do it for j, it's going to be minus 3 times t. So it's going to be minus 3t and then j. And then doing it for this one, I've got 1/2 times 2.4, right? Which I know is 1.2. And then I have to multiply by that t squared, don't I? So it's going to be t squared here. It's going to be I. And then plus, we've got 1/2 times j. So that's just going to be half j or 0.5j. So I'm going to write 0.5. And then we've got the t squared we need to multiply by. So it'll be t squared and then j. Now, let me put 4i plus cj here. Now we've got all of the i's separately and the j's separately. We can bring them together, right? So what we're going to do is pretty much when you do stuff like this, you're just basically going to treat the i's as factors and just factorize out the I. So I'm going to highlight all of the I components like this here, and then this one here. And then now if I was to take out an I from all of those, I'd have a bracket like this, and I'll have an I here, and then it's going to be 44 minus 16t plus 1.2t squared. And then plus, and then if I do the exact same thing for the j's, I've got this here, I've got this here, and I've got this here. Now, if I take out a j from all of those terms in green, I'm going to have a bracket like this. I have j on this side. It's going to be minus 10 minus 3t. And then it's going to be plus 0.5t squared, isn't it? And then we've still got 4i plus cj on the left-hand side. Now, remember, these two vectors are equal. If they're equal, it just means that the components are the same. So remember what we're trying to find. We're trying to figure out what the value of t is. So hopefully we can form some sort of equation in terms of t to solve. And you can do that quite easily because this component for the I here is 4. This has to be equal to this one here. So we can make these equal to each other, and that will give us our equation in terms of t, wouldn't it? And obviously we can do the same for c, which we're going to need to find anyway, but we need t first. So we're going to have to do it with the terms in blue. So we're going to have 4 is equal to 44 minus 16t plus 1.2 t squared. Now, if I move the 4 over, it's going to give me 0 is equal to 44 minus 4 is 40. So 40 and then minus 16t plus 1.2t squared. And then let me just swap the order just to get into quadratic. We have 1.2t squared minus 16t plus 40 is equal to 0. So what I can do now is just plug this into my quadratic solver to figure out what t is. And I've already started it here. We've got 1.2 here. And we've got minus 16 here, and then I'm going to put plus 40 here, positive 40. Put this here, and this will give me t is equal to 10. And then are there any other values? Yes, there are. There's 10 thirds, right? So we've got t is equal to 10 or t is equal to 10 thirds. Now remember though, they told us that t was greater than 5, isn't it? So since t is greater than 5, it can't be this one. 10 over 3 is 3.3 recurrent, isn't it? So you could just say since t is greater than 5, then therefore we could just say that t is equal to 10. And that would be our answer for part B. So now we've got our value for capital T. It says we need to find out what C is in part C, right? Now, if we know what T is, that's very easy now, right? Because remember, C is equal to this here, right? At any point in time for T. But we know T is equal to 10. So all we need to do is just plug in T equals 10 into here, and then that will give us C. So we can just say here, I'll just finish it off here for part C. And then we're going to say that we're going to say T is equal to 10, isn't it? So that means if I equate those, it's going to be C is equal to minus 10 minus 3t plus 0.5 t squared. So if I plug in 10 into there, it's going to give me minus 10 minus 3 lots of 10, and then plus 0.5 and then 10 squared. And I'll just put this into my calculator and see what it gives me. So plugging this in here, we go here, here. It's going to be minus 10 minus 3 lots of 10, and then plus 0.5 and then 10 squared. And this gives us 10, right? So therefore we could say that C is equal to 10. And that is question 4 finished. Now let's go into question 5. Okay, so question 5 says a small ball is projected with speed 28 meters per second from a point O on horizontal ground. After moving t seconds, the ball passes through the point A. The point A is 40 meters horizontally and 20 meters vertically from the point O, as shown in figure 2. The motion of the ball from O to A is modeled as that of a particle moving freely under gravity. Given that the ball is projected at an angle alpha to the ground, use the model to show that capital T is equal to 10 over 7 cos alpha for 2 marks. Okay, so this is not too bad. Remember, this is just a projectile question, right? And pretty much if you've had a look at the past paper questions that have come up, it's typically the same thing. They give you some sort of model, right? And they ask you a lot of show that's, right? Show that this is equal to that. And it's just about using algebra with your Suvat formulas, right? So what I'm going to do, I'm just going to screenshot uh, this diagram here. And I'll just put this here. And then let me also, oh, I've already got it here. And then let me also screenshot the show that what we need to show. Yeah. So I'm going to put this here. So we've got the diagram here already. And we need to show that t is equal to 10 over 7 cos alpha. Now remember, t is the time when the particle is at A. So this here is when t is equal to capital T, and we need to show that this is equal to that. Now remember, with projectiles, all you're going to do is just use your horizontal motion formulas and your vertical motion formulas to model the particle going from point O to A in this case. Now the show that has cos alpha in it and the time, right? Now for me, when I'm doing a show that, well, what formulas do I know that relates the time and cosine together? And that is just a horizontal motion formula for a particle going from one point to another. And we know that that's just equal to the distance, the horizontal distance it travels. So I'm going to say S, right? And this will equal U cos alpha T, right? Where U cos alpha is your horizontal component of the initial velocity, right? Now, in this case, we can see that the initial velocity was 28 meters per second. Now, remember, this is going to be my angle alpha here. Now, if I resolve this, this is going to be 28 cos alpha. And then this here is going to be 28 sine alpha, right? So our initial component of our velocity here is just going to be, I'm going to write I'll write ux, right, for horizontal movement. It's going to be 28 cos alpha. Now we know that we're modeling it towards capital T. So I'm going to say T is equal to capital T. And we know that it goes from O to A, which is 40 meters horizontally. So what I need to do here, just put T here. And then what I need to do is going to say S is equal to 40. So I'm going to plug this all into the formula and hopefully I'll get this on the top here. So this is just going to be 40 is equal to 28 cos alpha multiplied by capital T. And now if I divide both sides by 28 cos alpha, I'm going to get 40 over 28 cos alpha is equal to T. And then we can simplify the numbers here. Divide by 4 on the top, I'm going to get 10. Divide 28 by 4, I'll get 7. So I get 10 over 7 cos alpha is equal to capital T. And it's exactly what they wanted for part A. So yeah, that's done. That's 2 marks. And then now let's go into part B. Okay, so part B says show that tan squared alpha minus 4 tan alpha plus 3 is equal to 0 for 5 marks. Okay, so this isn't too bad, right? So remember what we did in part A. We showed that t is equal to 10 over 7 cos alpha, right? And we were modeling the particle moving from O to the point A, right? And we know that this had a horizontal distance of 40 meters, which we used in our horizontal motion model, right? Now, naturally, even if we don't really know what's going on here, we modeled the particle horizontally, right? How about modeling it vertically now? It just makes sense to do that, right? So what you want to do in this case, let me just do it here. So I'll do it on the next page, right? Part B, if I get this diagram here again quickly, right? Just copy this diagram here. Paste this here. Oops, where's it gone? Okay, over here to bring this down to the next page. So what we know from part A is that the particle, right, lands at the point A, right, when t is equal to 10 over 7 cos alpha, right? Now, we did that horizontally. Now, let's just do it vertically and see what happens. Now, what do we know at this point? Well, at A, we know that S is equal to 20, right? Now, we're going to model it horizontally. We're going to model it vertically, right? So I'm just going to put this here. Now, what do we know? We know that the height, I'm going to write S. I'm going to write SY because I'm just gonna just denote that we're modeling it vertically. This is equal to 20, and now I've chosen upwards to be positive, so the acceleration we know is going to be minus g. And what else do we know? Well, we know that u, right, which I'm going to call uy, this was going to be our vertical component of the initial velocity, right? Now remember, let's go back to our picture here. The horizontal component was 28 cos alpha, so naturally the vertical will be 28 sine alpha. So I'm just going to put this in. I'm going to say uy is equal to 28 sine alpha. And then now the time, right? The time, which I'm going to call capital T, we know is this expression here, 10 over 7 cos alpha, right? Now remember, let's not lose track of what we are trying to show. We're trying to show that tan squared alpha minus 4 tan alpha plus 3 is equal to 0. And I'm just going to bring this to our page so we don't need to keep going up and down again. So yeah, we need to show this here. And what you need to do, remember, we're just using Suvat now. Again, what formula do we know connects all of these variables together? S, A, U, and T. It's just S equals UT plus a half AT squared, isn't it? So if I just do this here, I'm going to say S is equal to UT plus a half AT squared. And then if I plug in everything that I know, then it's going to be S, which is 20. And this is equal to U, which is 28 sine alpha, multiplied by T, which is this expression here, 10 over 7 cos alpha, and then plus 1/2, and then A is minus G, and then T is 10 over 7 cos alpha, and then we're going to square this, aren't we? So what needs to happen now is that we just need to use algebra and some trig identities to get this expression here. Now, let us work with this to see what we can do. So I'll do it here. Now, if I tidy this up, right, I can see here that I've got, for this term, let me write the 21st, by the way. I've got 20 here. And then this here, I've got 28. I've got times by 10, that's 280. And then I'm going to do 280 divided by 7. These numbers in yellow will just give me 40, isn't it? It'll be 28 times 10, which is 280. 280 over 7 is 40. So this will be 40 here. And then I've got a sine alpha and a cosine alpha right here. Now, sine on the top, cos on the bottom, that's just tan, isn't it? So I can just write 40 tan alpha. And this is good progress because remember, we need an expression, an equation in terms of alpha. Now, continuing, what do we have on the in the last term? Well, what I would do in this case, I'm doing in green. I've got 1/2 and I've got minus g here. Yeah, so I'm going to just write this here. This is going to be, I can just take off the plus to be fair. This is going to be minus a half g. And then here I've got 10 over 7 cos alpha all squared. That is just the same as squaring 10 on the top and then squaring the denominator, which would be 7 squared is 49. Cos squared is just cos squared, isn't it? So cos squared alpha. So what I'd want to do to get the coefficient, right, the constant, all I'm going to do here is I'm just going to highlight everything in green here. This here with this and this. And I'm just going to put this directly into the calculator and and I'm going to see what it gives me. And when I do that, I've already got it here. Nice for us. 1/2 g, right, times by 10 squared over 49. This is equal to 10, right? So 1/2, yeah, that's perfect. So that's 10. So when I do that there, I'm going to have 20 is equal to 40 tan alpha. And then this is minus 10, right? And then this is going to be over cos squared alpha, isn't it? So we're here so far, right? So I'll just highlight this to be clear that this in green are the same thing. Yeah. All right. So we're here so far. Now remember to show that on the top here, we're trying to get tan squared alphas. We're trying to get tan alphas, right? Now remember, just like we saw in the stats paper, pure mathematics knowledge was needed. And we need it here as well. So we're dealing with trig identities, right? Now when I look at this here, I've got cos squared alpha on the bottom. Now remember your trig identity, 1 over cos squared alpha is just sec squared alpha, isn't it? So if I've got 10 on the top, that's just going to be 10 sec squared alpha, isn't it? So we could just say that this just becomes 20 is equal to 40 tan alpha, and then minus 10, and then cos squared alpha on the bottom, right, is just going to be sec squared. So it's just going to be 10 sec squared alpha altogether. Now remember, you're trying to get tans, right? We've got a sec squared. But remember, trig identities. You need to know your trig identities very, very well. Make sure you memorize them all off by heart. Because if you do, you would know that sec squared alpha is just the same as 1 plus tan squared alpha. So I can just replace that there. So I'm going to get 20 is equal to 40 tan alpha minus 10, and then I'm going to have 1 plus tan squared alpha here. And this is good progress because now we've got the expression all in terms of tan alpha. So what's left is just to expand and simplify it, and then hopefully we should get this result here. So let's go ahead and try and do that. So this way, we're going to get 20 is equal to 40 tan alpha minus 10 minus 10 squared minus 10 tan squared alpha, like this. And then now let us tidy up. Let's move everything from left to right. So if I do this, then I have equals 0 here. And then that minus tan squared alpha would be here, 10 tan squared alpha, like this. And then this 40 tan alpha would be minus 40 tan alpha. And then now I've got this minus 10, which I need to move over to the left, which will add 10. And I'll add it to the 20, that will be plus 30. So I get this here. Now remember, we need to show that tan squared alpha minus 4 tan alpha plus 3 is equal to 0. So all I need to do now is just divide everything by 10, don't I? So if I divide everything by 10, I'll just get tan squared alpha minus 4 tan alpha plus 3 is equal to 0 as required. And that will give you the 5 marks for part B. So now let's go into part C. Okay, so part C says, find the greatest possible height in meters of the ball above the ground as the ball moves from O to A for 3 marks. Okay, so remember with this one, the greatest possible height when you're dealing with projectiles is when the vertical component of velocity is 0. So all you're going to do here is just use your Suvat formulas. You're going to make the vertical velocity 0, find out where A is, and so on and so forth, and then just figure out what the greatest height is from there. So what I'm going to do is I'm going to model upwards as positive again. Now, what do we know? We know that the initial component of velocity, remember, was equal to 28 sine alpha. The vertical, I'm gonna use UI, by the way, UI, just to denote that it's vertical. The final velocity we know is going to be when it's 0, isn't it? Right. So we're going to say this is 0 here. We know that A is equal to minus G. And S is what we're looking for, isn't it? So we've got these here. Now, again, what formula do we know connects U, V, A, and S? It's just V squared is equal to U squared plus 2AS. So we've just got to put these into the formula here, and then that will give us our height, isn't it? We can rearrange for S. But before we do that, though, if you look at what we've got here, we've got 28 sine alpha, right? So for us to be able to work out what S is, we need a value of alpha, right? That we can put into sine. Now, remember in part B, we showed that tan squared alpha minus 4 tan alpha plus 3 is equal to 0. So alpha must come from here. So what we need to do is solve this for alpha, and then we can put that into there. So let me just write this equation again. So it was tan squared alpha minus 4 tan alpha plus 3 is equal to 0. Now, this is just a standard quadratic. 2 factors of 3, which add to make negative 4, will be negative 3 and negative 1, isn't it? So it's going to be tan alpha minus 3 and tan alpha minus 1 is equal to 0, meaning that tan alpha is equal to 3 or tan alpha is equal to 1. So what we have here is we actually have 2 options for alpha. Now let's read the question again. It says that we need to find the greatest possible height, and we can see here that there's actually 2 possible angles of projection. Now if we want the greatest possible angle of projection, right, or the greatest possible height, that would mean that we need the greatest angle of projection, wouldn't it? Right. So what we would need to do is just ask ourselves, well, which one of these gives us the greatest value? And it's going to be tan alpha is equal to 3. Now, what you can do is you could just do the tan inverse of both 3 and both 1 to figure out what alpha is for both, just to convince yourself that tan alpha is equal to 3. But tan alpha equals to 3 is definitely the larger value for alpha. So we're going to choose this one here. Now, what you can do, as I was saying before, you can take the tan inverse of alpha, out of 3, sorry, and then that will give you your alpha. Or since we're looking for sine alpha here, what I like to do is, because I don't like to round, I will just find an expression for sine alpha. And we can do this because if I have tan alpha is equal to 3, I can write this as 3 over 1, can't I? And then if I get a right angle triangle, alpha will be here. The opposite is 3. The adjacent is 1. The hypotenuse is just going to be the square root of 3 squared plus 1 squared, isn't it? Which is just the square root of 10, isn't it? So this is going to be root 10 here. And then now that I've got the hypotenuse, I could use a SOHCAHTOA just to figure out an expression for sine alpha and then plug that in instead. We know that sine alpha is the opposite over the hypotenuse. So therefore we could say sine alpha is equal to 3 over root 10. Now, we don't need to figure out what alpha is now because remember, uy is just 28 sine alpha, and we know that that's 3 over root 10. So you could do it like this. So what I'm going to do now is I'm going to use this formula here. I'll do it on the left here. I'll continue here. So we have v squared is equal to u squared plus 2as. And we know that v is 0. We know that u is going to be 28 sine alpha. So I'm going to write 28. And then sine alpha we know is 3 over root 10. So I'm going to write 3 over root 10 here. And then all squared, isn't it? And then plus 2. And then a is minus g. And then I've got s here. So we've got everything now that we need. So tidying this up, right? We could say that, well, this is just minus 2gs, isn't it? So I can move that to the left. This will give me 2gs is equal to all of this. 28 and then 3 over root 10 all squared, right? And then that would mean that s, the greatest possible height, would be 28 multiplied by 3 over root 10 all squared. And I'm going to divide this by 2g, or 2 times 9.8. So our answer for the greatest possible height is going to be whatever this is equal to. And I'm going to put this in my calculator and let's see what it gives us. So it's going to be put bracket here, 28 multiplied by 3 over root 10. 3 over root 10 all squared. And I'm going to divide this by 2 times g, which is 9.8. And this gives us 36 meters. So the greatest possible height is just 36 meters. This here is 36 meters. And that's part E done. And sorry, not part E, part C, right? Part D says the model does not include air resistance. State one other limitation of the model. Now, this one is always the one marker that's always at the end of these questions. They've told us that we can't use air resistance, right? What else could you use? Well, you could just say many things. You could say the ball is modeled as a particle. What if it will have rotational symmetry? You could say the wind. What else could you say? You could say the spin of the ball. Maybe G could be 9.81, more accurate instead of 9.8, and so on and so forth. So it's just one of those things that you can use for that answer, and that will give you the 1 mark for part D. And yeah, that's pretty much done. That's question 5 done. And now let's go into question 6. Okay, so question 6 says a rod AB has mass M and length 2a. The rod has its end A on rough horizontal ground and its end B against a smooth vertical wall. The rod makes an angle theta with the ground as shown in figure 3. The rod is at rest in limiting equilibrium. Part A says we need to state the direction, left or right on figure 3 above, of the frictional force acting on the rod at A. Give a reason for your answer. This is 1 mark. Okay, so this is not too bad. So let's just screenshot this. Let's get the rod going here. Let me just put this underneath her. Just like this here. And then now we know, or we don't know actually, but with moment questions, right? Whenever you're doing these types of questions whereby you've got a rod here or a ladder, it's this type of setup, right? There's always going to be a reaction force at B, right? Where the wall and the rod are meeting. And it's going to be perpendicular to the vertical wall, isn't it? Yeah. So we're going to have a force, a reaction force going this way. And this is called RB. Now, they've asked us to show or to state the direction of the frictional force. Now, this is rough here. So we've got this here, and the frictional force is either going to act this way to the left, or it's going to act this way to the right. Now, remember, they did tell us that this is in equilibrium. Now, we know that this force is acting this way towards the left. For it to be in equilibrium, for it to balance out, the frictional force has to be going in the opposite direction, isn't it? Right? For it to be in equilibrium. So that means that we have to rub out this part, don't we? We have to rub out this part here, and F is just going to be F is just going to be acting towards the right. So what I'm going to do here is going to put this here. So we know that this is how the friction force is directed. It's acting towards the right, towards the rule, because it has to balance out with the reaction force acting towards the left. So for part A, for the 1 mark, you could just say that F must act towards the wall, or to the right, as RB, the reaction force at B, acts to the left. Yeah, something along those lines will give you the 1 mark. Another way that I like to think of it as well, right, is if you think about it logically, right, it's in equilibrium. The moment it's not in equilibrium and this starts to move, this part will go downwards, isn't it? This part of the rod will go downwards, isn't it, due to gravity, meaning that this part A will go that way. And if it goes that way, the friction will have to go in the opposite direction because friction opposes motion. That's another way you can do it as well. So that is that, and that will give you 1 mark for part A. Now let's go to part B. Part B says the magnitude of the normal reaction of the wall on the rod at B is S. In an initial model, the rod is modeled as being uniform. Use this initial model to answer parts B and C and D. It says by taking moments about A, show that S is equal to a half mg cot theta for 3 marks. Okay, so we're taking moments in part B. So what I'm going to do, let me screenshot the question so I don't need to keep going up and down. So I'll put this here. It's this here. And let's get the diagram going again. So we'll take a moment. So we need a force diagram now. Or we've got one here, but it's partially completed. We need to finish it off. Okay. So let us put this here. And what did they tell us? They've told us, let me just move this a bit here. They've told us, whoops, to go down here. There. Okay. Where are we? Yeah, we're right here. So let me go here again. And what have they told us? They've told us that in this model here, right? They've told us, or we know from part A, that we have a reaction force acting this way, which we know is called S now. We know that the frictional force acts in the opposite direction, F. Now, in part A, or in the question, they told us that this rod is uniform. They said it right here. Now, if it's uniform, it means that the mass, right, or the weight acts down the middle, right? So that means that we're going to have a point here, which is in the middle, and we're going to call this point, we're going to call this force the weight. The mass is M, and the weight must be mg, right? So that's fine. And then another thing as well is, remember, we have a point of contact. This rod is in contact with this surface here. So there must be a reaction force, isn't it? So I'm going to call this R, and I'll call it RA. So these are our forces here. And also as well, they told us that A to B is 2A, didn't they? So this is 2A. Now this whole thing is 2A. Now, we need to take moments about A. Now, remember, whenever you take moments about a specific point, it means that you can just ignore the forces acting at that point, isn't it? So the only forces that we need to worry about is the S and the mg. The RA and the F are going to be disregarded if we're taking moments about A. Yeah, because they're disregarded. Anyways, so let us have a look. Now, remember, when you're taking moments, it's in equilibrium. So we have, we're going to have clockwise forces and we're going to have anti-clockwise forces, right? And we know that they have to be equal if they're in equilibrium. So what we're going to do is we're going to take moments, right? Now, remember, whenever you're taking a moment, the definition of a moment is just the force multiplied by the perpendicular distance, isn't it? So what I'm going to do, if I start with mg, what I like to do when I'm doing moments questions, right, is I'm going to extend this line like this, right, just to show me the direction in which it's traveling. It's just traveling vertically downwards. Now, A is right here. Now remember, the moment is defined as the force multiplied by the perpendicular distance. So what I could do is if I put a right angle right here, and that will be one because this horizontal is vertical, we have a right angle here. The perpendicular distance of this force mg is this distance here, isn't it? Let me just make this a bit thinner actually. It's this distance here. So what I like to do is say, okay, fine. I know that the answer then, right, is going to be, hold on, let me get my pen. It's going to be that force times by that distance. And let's just see whether or not it's clockwise or anti-clockwise. The force is acting this way. I need to get to A, so I need to swing around that way. I need to swing this force around that way. And that is acting in the clockwise direction, isn't it? This is clockwise. So I'm going to put this here. These are equal. And we've got the clockwise. So it's going to be mg, that's the force. And I'm going to multiply by this distance in blue, whatever that distance is. So what I like to do is I'm going to get another triangle, right? And this is just going to be for the distance. So that point there, I'm going to just draw this here, like this. And what can we say? This is theta right here. And what else do we know? This is the point A that we're dealing with here. So I wrote point A. And I need to work out what this distance is right here. Now remember, they've told us that this entire distance A to B is 2A. So this distance here, if I call this, for example, X, right? A to X is just going to be half of 2A, right? Which is just going to be A. So now we have everything we need. We can just say, well, you know, from Sokotowa, this is just going to be A cos theta. The adjacent is going to be A sine theta, isn't it? Meaning that the distance in blue, the one that we're looking for, is right here. This is just going to be A cos theta. So therefore, the moment, the clockwise moment, is going to be the force mg multiplied by that blue distance, which we know is A cos theta. So I'm going to put that there. So that's done. We've got the clockwise force. Now what's left is to figure out the anti-clockwise, which has to be S, isn't it? So again, what I like to do is, this is the force, this direction it's acting in. I'm just going to extend this line here. So let me do it like this here. If I extend this line like that, we can see that this force is just acting in this direction. And I like to do it so it goes past the point where we're taking moments about, right? And you're going to see why. So let me just move this here and let me make this a bit lower just so it's clear, right? And this is the force S. Yeah. Now remember again, the moment is the force multiplied by the perpendicular distance. We can see right here, this is the point A. We can see a perpendicular distance is just going to be this distance right here, isn't it? Because I can put a right angle here. And then now this is going to swing this way to get me to A. And we can see quite clearly this is anti-clockwise force, right? This anti-clockwise direction. So therefore we could say that the moment is going to be the force, which is S, and it's going to be multiplied by whatever this distance here is in green, right? And if I look at this distance here is exactly this distance here, isn't it? Now I'm going to just draw another triangle just so it's very, very clear. So it's super, super clear. So I'm going to get this here, and then I'm going to put this like this here. And then this is going to be the point A. This is theta. This is the point B. We know that this entire distance A to B is 2A. Yeah? 2A. And this is a right angle here, and we're looking for this distance here. Now again, if this was A cos theta, this is going to be 2A cos theta, meaning that this one is going to be 2A sine theta. So the distance that we want, which is in green here, right, which is this one here, these two are the same, is 2A sine theta. So I can label this distance here, and I'm going to say that this is 2A sine theta. So that means that the moment, the anti-clockwise moment, is going to be the force S multiplied by that distance in green, because that's the perpendicular distance to A, which is going to be 2A sine theta. So I get this equation here. Now remember what we're trying to show. This is to show that question. We're trying to show that S is equal to half mg cot theta. Let me just move these triangles out of the way. So I'll just finish it off here. Move these here. I'm going to just move these to the side here. So now we are here. Let me just put this here. Okay, so now just to tidy up a bit more, we need to get S on its own. So what we can say then is, well, if I want to get S on its own, we can just divide by that 2A sine theta, isn't it? So we're going to have mg A cos theta divided by 2A sine theta. And this is equal to S, isn't it? Now, when I look at this, I've got a division of 2 on the bottom here. I can write that as a half. So I'm going to say S is equal to that division of 2. I can write as 1/2. These A's right here, they're going to cancel, aren't they? So I can cancel them. So it'll be none of those. And then I've got this mg here, right? So right now I've got a half mg. And then right now, to finish off with, I've got cosine over sine. We know that this is just cot theta from our trig identities. So therefore we get S is equal to half mg cot theta as required. And that will give you the 3 marks. And that is our part B done. So now let's go to our part C. Okay. So part C says the coefficient of friction between the rod and the ground is mu. Given that tan theta is 3/4, find the value of mu for 5 marks. Okay, so it is 5 marks, so it seems like it's a lot, but don't worry, this is pretty straightforward, right? Now, you're doing an exam, it's asking you to find the value of mu. Well, where do you know mu comes up in the mechanics? It's just F is equal to mu r, right? So the first thing I will do is say, okay, well, fine. I know I'm trying to find out what mu is. I know that F is equal to mu r. Well, mu is just equal to, if I rearrange this, we can just say that mu is just equal to F divided by R. So all we need to do here is just work out what the frictional force is, work out what the reaction force is, and plug those in, and this will give us our answer. Now, in this case, remember, mu is the coefficient of friction between the surface, right? So it's going to be RA, right? Technically, I'll write RA because that's the reaction force. I've labeled it RA here, so I'll be consistent. Right. Now, what do we do to figure out these here? Now, first things first, let's resolve, right? So if I resolve, for example, horizontally first, we could see that from our diagram, we could see that this frictional force here has to be equal to this reaction force at BS. So we could just say that F is equal to S, right? But remember though, in part B, we showed that S is actually equal to a half mg cot theta. So in other words, we could just say that F is just equal to a half mg cot theta, right? So we know what F is. That's fine. Now let's resolve vertically. Now, if I resolve vertically, we can see quite clearly that this reaction force RA, right, has to be equal to this force mg here. So I could just say that RA is just equal to mg. So with that being said, we've got our expressions for F and RA. That must mean that mu would be equal to F, which we know is a half mg cot theta, divided by RA, which we know is mg. So this is mu. Now we just need to simplify. Okay, so what do we have here? Now, I've got two mg's top and bottom. This mg is going to cancel with this one. So therefore, I'm going to have this here and this here. And that means that mu is equal to 1/2 cot theta. Right? Now, remember, they told us that given that tan theta is 3/4, right? They've told us that tan theta is 3/4. So we could say that tan theta is equal to 3/4. We know that cot is just a reciprocal of tan. So that means that this is to be equal to 4/3, right? 4/3. So in that case, we could just say mu is equal to 1/2 times by 4/3. And in this case, this is just 4/6, which is just 2/3. So therefore, we could say that mu is equal to 2/3. And that's that. That's the 5 marks done. Okay, so that's done. Now let's have a go at part D. For 3 marks, it says find, in terms of M and G, the magnitude of the resultant force acting on the rod at A. Okay, now when we look at the rod at A, we've got two forces. We've got a horizontal force of the friction, and we've got a vertical force, the reaction, right? The magnitude of this resultant force is just going to be the Pythagoras of these two components of forces here. So in other words, I'm just going to say, if I call the resultant force R, right, like this, it's just going to be equal to the magnitude, the square root of these two, so F squared plus RA squared. Right, so that's all we're going to do here. So for part D, have I got enough room to do it here? Yeah, I'll just continue here. So part D, we can say that the magnitude of the resultant force at A is just going to equal F squared, right, plus RA all squared. And then plugging this in, well, F squared, remember F, we know was a half mg cot theta, isn't it, right? So I'm going to have a half mg cot theta all squared, like this. And I'm going to plus the reaction force, which was just mg, yeah? So it's going to be mg squared. Okay, so we're here. We need to just simplify this, don't we? So tidying this up a bit, if I square this expression here, I'm going to have 1/2, which is going to square to be 1/4. This mg is going to square to become mg squared. And then the cot theta will square to be cot squared theta. And then plus mg squared. Now remember, we know that cot theta is 4/3, isn't it? So to get cot squared, I'm just going to square that, which will just give us 16/9, right? So we could just say this is just going to become 1/4 and then mg all squared. And then cot squared is 16/9, 16/9, like this. And then plus mg squared, isn't it? Like this. Now tidying this up here, what do we get? Well, what do we have here? We've got a quarter. We've got 1/4 here, right? And we're timesing it by 16/9, right? The 16 and the 4 will make a 4. This will just be 4/9. This is going to be 4/9 mg squared, like this here, and then plus the mg squared. So we're here. Now, can we tidy this up a bit more? We can. They're both like terms. They're both mg squareds. So what we can do here, let me just finish off here. So we've got 4/9 mg squared plus mg squared. Now remember, mg squared is just the same as 9/9, isn't it? 9/9. Meaning that I can just tidy this up to become 13/9 mg squared. And then we could just tidy this up a little bit more. Did they want it in a specific form? No, but we can tidy this up a little bit more because remember, from our surd laws, we can just separate this into two surds like this. We could write this as root 13/9 and then mg squared like this. Now this one on the right is very simple. This is just going to become mg like this. And then this one from our surd laws, we can say this is the same as the square root of 13 over the square root of 9. So therefore, we could just tidy it up and say that this is just equal to root 13 over 3 mg. So therefore, the reaction at R, the resultant at R, sorry, will just be equal to root 13 over 3 mg. And that will give you 3 marks for part D. Now let's go into part E. Okay, so part E says in a new model, the rod is modeled as being non-uniform, with its center of mass closer to B than is to A. A new value for S is calculated using this new model with tan theta equal to 3/4. State whether this new value for S is larger, smaller, or equal to the value that S will take using the initial model. Give a reason for your answer for 1 mark. Okay, so for me, think this is not the most straightforward one marker, but what I would do is just maybe attempt to calculate a new value for S, right? So what I've got here, just underneath, is I've just got a little bit of what we did in part B when we took moments, right? And this is what we had initially, right? We figured out that S was equal to half mg cot theta. Now remember, this is when the center of mass was in the middle, right? When it was uniform. So if it's closer to B now, then what you could say is maybe, for example, if I was to move this here, let's say I made it 3/4 of the way. So let's just say it was here now, the center of mass, right? Mg would be here. And then this would be 1.5a, wouldn't it? And then this would be 0.5a. Now, if I was to take moments, right, how would that affect S? Well, remember, S was equal to this here. So what we could do is say, okay, well, fine. If I was to take moments again, then what will happen is that the perpendicular distance now is going to be this one right here, isn't it? It's going to be this right here. And we can see quite clearly that that distance here is just going to be 1.5a cosine theta. So now, if I compare this with what I did originally, remember at the top, this is a uniform model. It was a cos theta, right? When we took moments about the weight, about a for the weight, it was a cos theta, right? Because it was in the middle. Now it's 1.5a cos theta. So what I can do here is I'm going to replace this here with 1.5a cos theta. 1.5a cosine theta. Now, if I want to get S from here, then we could just say S is just going to be equal to mg times 1.5a cos theta. And then we will just divide this by the 2a sine theta, isn't it? 2a sine theta. And then doing this here, well, we've got 1.5 divided by 2, right? That's 0.75 or 3/4. So I'm going to have 3/4 here. And then I've got the mg. And then I've got the a's will cancel. The a's will cancel. And then I've got cot again. So this is our new value for S, right? Now remember, this is when it was non-uniform. So what's happened here? Well, let's compare both S's. Well, the uniform model had a half, right? This is 0.5. The non-uniform model, when the center mass was closer to B, it was 3/4, so it's increased, right? So as the center of mass gets closer to B, S will increase. So what you could just say here, just for the 1 mark, is S would be larger. S would be larger as the moment of the weight about A would increase. About A would increase. And that will give you the 1 mark. I'm not sure if you have to do all of this here. Maybe you guys can see it straight away, but I think for me anyway, and explain it to you, I think it was best to just draw a diagram and just explain it like this. But yeah, that's pretty much it. And that's mechanics finished. Hi guys, Daniel here. Hope you're doing well. So yeah, we've made it to the end of paper 3, end of mechanics, which concludes the entire of applied and the entire of A-level maths for June 2023. So hopefully you didn't find the papers too bad, and any questions that you did find tricky or a bit difficult, hopefully these videos have helped you understand them a lot more, and you're in a better position for June. And yeah, if you found these videos helpful, then yeah, just feel free to drop a like, comment, subscribe, share with your friends, anyone that you think would benefit. And yeah, again, wishing you all the best of luck for your exams in June. You're going to smash it. Just remember, please start your past papers if you haven't already. That is the main thing. That's the best way to get a good grade. Just do lots of past papers, time yourself, mark it on your own, and then just see how you're getting on. But yeah, again, best of luck for June. And yeah, see you soon. Take care. Bye bye.